In our last lecture, we developed the energy equation, which we can use to close the system of equations for fluid dynamics when we don't have a barotropic equation of state. Now, as part of that, though, we introduced another parameter that we have to manage, which is this Q cool, which is the cooling function, which can be either positive or negative depending upon whether it has heating or cooling for our medium. So rather than go through the details of what are in those cooling functions, and those are typically things that astronomers would look up, find the cooling function for the scenario that they're interested in, I at least want to talk about what kinds of things produce cooling and heating in the universe. And I mentioned a few of them. I mentioned radiation, convection, and conduction in the last lecture. In this lecture, I want to just build on those a little bit and give you a few examples and talk about how they come about and where we would care about them. So, examples of heating and cooling. So some examples of heating and cooling are, the first one I want to talk about is cosmic rays. So cosmic rays are an important source of heat in the interstellar medium. And cosmic ray heating comes about through high energy particles, which collide with atoms. They cause ionization, and those free electrons carry excess energy with them, and that is heating. So high energy particles cause ionization. And you have excess energy in the free electrons. And the rate of cosmic ray heating is proportional to the cosmic ray flux times the density. So the more cosmic rays you have in a medium, or the higher the density of that medium, then the higher the heating rate. And this is in particular case where it's particularly important is in the interstellar medium, where cosmic rays are a big source of heating for the interstellar medium. So a second source of heating is via conduction. So in conduction, what we have is the transport of thermal energy through diffusion of free electrons to cooler areas. Conduction is something that we're all pretty familiar with. I mean, we think of metal as being highly conductive. The idea being that you have kinetic energy associated with your free electrons. If they're hot, then they have a lot of kinetic energy. They move into a cooler area and they transfer some of that. And what we end up with is that the heat flux, which is the rate of change per unit volume of the energy, so the heat flux, which is given by the divergence, the conductive flux, is equal to some constant times grad squared of the temperature. And this is seen in not a lot, it's not important, I guess that is to say, in a lot of astrophysical situations, but it is important inside white dwarfs, which do show some conduction, and that is a major source of energy transport in them. The third situation is convection. So I cleverly wrote this out in advance. The convection is something that we're going to develop in a couple of lectures ahead of now, where we're going to work on the convective instability. But it's the idea that you transport energy due to fluctuations or circulations in the presence of a temperature gradient. This is really important inside massive stars and also inside planets, where you have a temperature gradient from the interior to the exterior. Imagine the sun, it's extremely hot inside, it's cooler at its photosphere. And by having circulation of fluid, you can convect heat from one portion of the star to another. And it's an important process for those stars. And the fourth form of heating and cooling that's very important, and particularly as a form of heating, is radiation. And of course, we've spent most of our semester talking about radiation. So we know a lot about radiation and about how it transports energy. So the idea here is that you have photons, or obviously EM waves, which can carry energy from one place to another, and that can result in heating of another fluid. So for example, imagine that you have a star. It's producing ultraviolet photons. Those photons come away from the star and they interact with gaseous medium surrounding the star in the form of a nebula, and that can transfer energy from that star to the nebula, and therefore that is heating the gas of that nebula. It's heating that fluid. And common ways of seeing that are, you see it via recombination, which we've talked about in our lectures. Free emission and line emission are all things that you're very familiar with and can imagine how those are important as sources of heating. So that's as far as we'll go with heating and cooling in these lectures. As I said, in general, astrophysicists would consider what situation they're dealing with. They may be considering the interstellar medium and want to know what the temperature of that gas is, and they'll consider what kind of cosmic ray heating there is. They'll look up a heating function for that, and they'll also look up what the radiative heating is, and you would work from there. And we'll stop with that lecture here.